In order for muscles to function, they have to have ATP. ATP is the energy they need for contraction. Muscles have just a little bit of ATP stored in them. This is consumed in 4 to 6 seconds of contraction. That means that the muscle has to have mechanisms for generating its own ATP, and there are 3 basic pathways for doing this. One is through direct phosphorylation, using a stored molecule called creatinine phosphate. Then there is anaerobic glycolysis, using glucose without the presence of oxygen, and aerobic respiration, breaking down glucose in the presence of oxygen. In direct phosphorylation, there is a molecule stored in the muscle called creatine phosphate. Creatine phosphate has a phosphate molecule on it that is a high energy bond. The cell cannot break that phosphate off and harvest the energy. Instead, we have to transfer the phosphate from the creatine phosphate to an ADP molecule to make ATP and creatine. Creatine phosphate is stored in the muscle at a higher level than ATP is stored, but it's still exhausted after about 15 seconds of contraction. In anaerobic glycolysis, we have glycogen stored in the muscle, and glycogen can be broken down to glucose. Glucose can then undergo glycolysis, and when we undergo glycolysis, we make a couple of ATP and we make pyruvic acid. This process does not require oxygen. Now you might think that since muscles have such a great blood supply, why would they ever be without oxygen? If you have vigorous muscle contraction start very quickly, it will compress the capillaries in the muscle, and this will limit the amount of oxygen delivered to the muscle tissue. We also produce lactic acid. If lactic acid remains in the muscle, it can make the muscle stiff. Lactic acid can be released to the blood and taken to the liver, where it can be converted back to pyruvic acid, and we can reuse that to make more ATP. About 5% of the energy that we can get from a glucose molecule can be yielded through anaerobic glycolysis, and it happens very quickly. It happens 2.5 times faster than aerobic respiration. However, this form of ATP production will only give us about a minute's worth of activity. Aerobic respiration is when we take that glucose that's been broken down to pyruvic acid and we run that pyruvic acid through the mitochondria, through the Krebs cycle and the electron transport system. Here we will make water, carbon dioxide, and up to 32 ATP. Glucose, glycogen, fatty acids, and pyruvic acid all provide fuel sources for this process. As a matter of fact, fatty acids are the main fuel for muscle activity after about 30 minutes of exercise. Now, this process does require oxygen and does occur in the mitochondria. There are many chemical steps involved here, so this is a slow process, but it does give us a lot of ATP. 95% of the ATP we can harvest from a glucose molecule is harvested in this manner. So if we look at how long we can run, the stored ATP is used up pretty quickly, then the stored creatine phosphate is used up, and then if we're operating under anaerobic glycolysis, we run out of energy in about a minute. If we can convert to aerobic respiration, here we're making lots of ATP, we're using it slowly, then we can sustain muscle activity for several hours. That direct phosphorylation using creatine phosphate is useful for surge of power activities, things like weightlifting or diving or sprinting. Anaerobic glycolysis is useful if you're doing activities that have on and off bursts of activity, things like soccer or tennis or a 100-meter race, things where you're going to demand energy for a short period of time and then you're going to rest and then you'll demand activity again. But aerobic respiration is required for prolonged activities. This is the endurance of exercise. Jogging, marathon running, even standing upright for long periods of time require aerobic respiration. Aerobic endurance is the length of time the muscle can continue to contract using the aerobic pathway. It allows for light to moderate activity which can continue for hours. Your anaerobic threshold is the point at which the muscle is going to convert over to the anaerobic pathway. Now, once you've done this, you're going to fatigue in 1 to 2 minutes. You sometimes see this happen in the Olympics or other televised races. You will see marathon runners, and they'll be going along at their constant speed for a long period of time, several miles, and then they will enter the stadium where they have to do that last lap before they cross the finish line. They will put on that last burst of activity. They will hit their anaerobic threshold and they'll go into anaerobic respiration for that last little burst of activity. If they time it right, it gives them that little push to get ahead of the guy in front of them and cross the finish line. If they don't time it right, they run out of ATP and they go into contracture. They make cross bridges, and because there's no ATP to break them, those muscles are contracted or cramped. Muscle fatigue is a physiological inability to contract even when the muscle has been stimulated by a nerve. ATP production can't keep up with ATP use, and your glycogen stores have been depleted, so you don't have the ability to make more ATP. Also, lactic acid will accumulate. This will decrease the pH in the muscle and will interfere with ATP production. Now, lactic acid accumulation probably contributes to psychological fatigue, that idea that I could contract one more time, but I just don't want to. Ion imbalances occur because we need ATP to run the sodium-potassium pumps to repolarize the membrane. If those can't function, then we can't repolarize the sarcolemma, and that means we can't depolarize it again. We can't send a signal to make it depolarize. Most muscle fatigue is really psychological. The muscles can respond, but we just feel tired and we don't want to respond. If we truly run completely out of ATP, then we have contractures. We need ATP to break cross bridges. Without that, we're kind of like we're in rigor mortis. Those muscles are contracted and they can't relax. The cross bridges can't detach. This can lead to muscle cramps. Even after we finish exercising, the body continues to need oxygen. We have to restore cellular chemistry. Glycogen stores have to be replaced. So we have to take glucose and build it back into glycogen. That is a chemical process that's going to require ATP, and we use up oxygen when we make ATP. We have to restore the myoglobin stores, so some oxygen will have to go back into the muscle tissue and attach to the myoglobin. We need to convert the lactic acid back to pyruvate in the liver so that we can run that through the Krebs cycle. That's going to take ATP, and we need oxygen to make ATP. We have to restore the creatine phosphate, so we're going to reverse that process. We'll take ATP and use it to phosphorylate the creatine to get creatine phosphate back. And we have to restore our ATP reserves. All of these things require oxygen, so our need for oxygen, our metabolic rate, is elevated for several hours after we finish exercising. Only about 40% of the energy we produce actually accomplishes work. The remaining energy is released as heat. We do have homeostatic mechanisms that help cool the body during exercise. We sweat so that sweat evaporates and that cools us down. On the other hand, if we're cold, we generate heat by muscular activity. Shivering is one form of muscular activity, but we may also wave our arms around, jump up and down, walk in place, do other things to build some heat with our muscular activity. Muscles don't always contract with the same force. The force of muscle contraction is dependent on the number of cross bridges we form in the muscle. This has to do with the number of fibers stimulated, that recruitment process, with the relative size of the fibers, and these cells can hypertrophy. They can increase in size and thus increase in strength. It's controlled by how often we stimulate the muscle to contract, and finally by the degree the muscle is stretched. So here we see the number of fibers recruited, the size of the fiber, the frequency, and how stretched the muscle is. The number of muscle fibers has to do with motor unit recruitment. The more we stimulate a muscle, the more motor units get recruited. The more motor units that are recruited, the stronger the contraction. Muscle fiber size means that there will be more myofilaments to be involved in contracting. Hypertrophy is an increase in the size of muscles. This is caused by exercise. When muscles get bigger, the cells themselves are getting bigger because they're getting more sliding filaments packed into them. They don't increase in number, just in size. If we stimulate a muscle more frequently, we're going to sum up all of those contractions. That's going to make the muscle contraction stronger. And finally, the degree of stretch. There is a length-tension relationship. A slightly stretched muscle will contract more strongly than one that is not slightly stretched. It is ideal to have the thin and thick filaments just barely overlap. That way the myosin heads walk the entire length of the actin molecule, causing the contraction. If they are completely stretched so that there is no overlap, then muscle contraction can occur because we can't make cross bridges. There are different types of muscle fibers. We can classify them based on their speed of contraction and how they form ATP. When we look at speed of contraction, we either have slow fibers or fast fibers. This is determined by how fast myosin ATPase will split ATP to recock that myosin head. Some fibers split ATP very slowly, so the head recocks very slowly. Others split it very rapidly, and so the head recocks very quickly. The ATP forming pathways are the oxidative fibers. These are fibers that rely on aerobic respiration, so they make lots and lots of ATP. Glycolytic fibers rely on anaerobic glycolysis. They produce the minimal amount of ATP. So basically there are three muscle fiber types: slow oxidative fibers, fast oxidative fibers, and fast glycolytic fibers. Slow oxidative fibers contract slowly. They have an increased oxygen delivery because they rely on oxidation. They rely on aerobic respiration. There's lots of blood, there's lots of myoglobin, so there's a good oxygen supply. Because myoglobin and blood are both red, these fibers are sometimes referred to as red fibers. This type of muscle fiber is fatigue resistant. It has a very high endurance level. There are lots of mitochondria because mitochondria is where oxidation occurs, and there's not a whole lot of stored glycogen. We're going to deliver glucose to the muscle in that rich blood supply. These muscles don't have a lot of power. They are mostly your posture muscles. The fast oxidative fibers contract very, very quickly. They also rely on aerobic metabolism, so they have a good blood supply and they have lots of myoglobin. They're classified as red fibers. They have a high number of mitochondria, and they have a moderate level of glycogen storage. We do have some stored glucose in the cell. They're moderately fatigue resistant. They have intermediate power. These are the muscles you use in walking or sprinting or those kinds of activities. The fast glycolytic fibers contract quickly, but they rely on anaerobic metabolism. As a result, they don't have a whole lot of myoglobin, they don't have a really rich blood supply, and they don't have much of a need for mitochondria. They have all of these things, but they don't have them like the red fibers do. They do rely a lot on glycogen stores, so they have an increased amount of glycogen storage. This makes them appear white, so these are sometimes referred to as white fibers. Because these fibers split ATP quickly and then rely on anaerobic respiration to make their ATP, which doesn't make a whole lot of ATP, these fibers will fatigue very easily. They are very powerful, but they're only good for short-term kinds of contractions, things like hitting a ball. In terms of your muscle fiber type, usually it's a mix of all three types. The ratio of fibers is typically determined genetically. This is why some people may be more athletically inclined than others. Their composition of muscle fibers may be just right for certain activities. Marathon runners would naturally have a lot more slow oxidative fibers. Sprinters would have more fast oxidative fibers in their muscles. And weightlifters, kind of equal amounts of fast and slow oxidative fibers. Now, with training, you can alter your muscle composition. When you exercise, the activity will increase the size, the strength, and the endurance of your muscles. If you are inactive, you will lose mass and strength, and the muscles may even atrophy. When a muscle atrophies, it has lost so much mass and strength that even if stimulated, it can't respond. There are different types of exercise that can help you with your muscle activity. There are two basic types of exercise. Endurance exercise is your aerobic exercise. Here you will increase capillary number and the number of mitochondria in your cells. Remember, mitochondria can divide if there is a demand for energy in the cell. The fibers will begin to make more myoglobin so that you'll have more oxygen storage capability, and this will result in very efficient muscle metabolism, greater endurance, greater strength, and more resistance to fatigue. You may convert fast glycolytic fibers into fast oxidative fibers. Endurance exercises would include things like swimming, jogging, and biking. Resistance exercise is anaerobic exercise. Here muscles hypertrophy. The size of the muscle fibers increase, not the number of muscle fibers. Here we will see increases in the number of mitochondria, myofilaments, myofibrils, and connective tissue between the cells. This resistance kind of exercise puts a lot of stress on the muscles, and so we strengthen the muscles with connective tissue. These muscles will begin to store more glycogen. We see this with weightlifting and with various kinds of isometric exercises. It's usually best to use a balanced exercise program. Muscles respond on what's called the overload principle. You have to force the muscle to work hard to promote increased muscle strength and endurance. Muscles will adapt to the increased demands placed on them. You have to overload the muscles if you want further gains. Overuse injuries can result if you don't allow appropriate rest in between bouts of exercise. The best program is to alternate aerobic and anaerobic activities, something that's called cross-training. Disuse atrophy occurs if the muscle is not used, if the muscle is immobilized. This happens when someone has their arm put in a cast because they've broken a bone. Muscle strength declines 5% for each day the muscle is immobilized. Without neural stimulation, muscle will atrophy to 1/4 of its initial size. It will get that much smaller. Fibrous connective tissue will replace most of the lost muscle tissue, and when this happens, rehabilitation is impossible. There's just not enough muscle tissue to respond. Neural stimulation loss usually is the result of nerve damage, and this is one of the things that causes paralysis. Another type of muscle tissue we have is smooth muscle. This is found in the walls of most hollow organs, except the heart, which has cardiac muscle, and usually is 2 layers. One layer runs longitudinally, the length of the tube, the other runs circularly. Smooth muscles are spindle-shaped fibers. They're thin and short compared with skeletal muscle fibers. They usually have only one nucleus and they don't have the striations. That's why they're called smooth muscle. There's not very much connective tissue in smooth muscles, just a little endomysium. The sarcoplasmic reticulum is less developed. It still releases intracellular calcium, but there are pouch-like enfoldings on the sarcolemma. These are called caveolae, and they hold little pockets of extracellular calcium. So when these muscles contract, we will rely on both intracellular calcium and extracellular calcium. Most of the calcium comes from outside the cell, but it can enter very rapidly. There are no sarcomeres, there are no myofibrils, and there are no T-tubules. There's a different arrangement of actin and myosin. When we look at the nervous control of smooth muscle, we don't have neuromuscular junctions as we saw in skeletal muscle. Instead, these muscles are served by autonomic nerve fibers. These nerve fibers contain varicosities, little swellings all along the nerve, and the varicosities are what stores and releases the neurotransmitter. In the autonomic nervous system, we have both acetylcholine and norepinephrine as neurotransmitters. So on this sheet of smooth muscle, here is an autonomic nerve fiber, and notice how we don't have axon terminals, but rather all along the fiber, we have these varicosities. And we have the synaptic vesicles in all of the varicosities. The myofilaments in smooth muscle have a different ratio of thick to thin filaments. It's a ratio of 1 to 13. In skeletal muscle, that ratio is 1 to 2. The actin fibers spiral around the myosin, which is why there are so many actin fibers per myosin fiber. The cells, when they contract, sort of twist up in a corkscrew type manner. The thick filaments have myosin heads along the entire length of the fiber because they have actin along the entire length of the fiber. There is no troponin complex, however there is tropomyosin on the fibers. There are dense bodies scattered in the sarcoplasm. These help anchor the non-contractile intermediate filaments to the sarcolemma at regular intervals. This is important in the way the smooth muscle contracts. Calmodulin is a protein that's found in the sarcoplasm. It's going to bind calcium. Now when we see our smooth muscle, here we have the little caveolae, these little end pouches. These are the dense bodies, a single nucleus, and you don't see any striations because we don't have that overlapping of myofilaments. When the smooth muscle contracts, it really does corkscrew up. It can get much shorter than a skeletal muscle as a result of this activity. Smooth muscles display slow, synchronized contractions. The cells are organized in sheets and so they contract as a unit. The cells are coupled by gap junctions. This means that when we disrupt one cell, all of the cells get the message simultaneously. So action potentials are transmitted from fiber to fiber via the gap junctions. Some cells in smooth muscle are self-excitatory. They're sometimes called pacemaker cells. These cells are capable of depolarizing on their own without being stimulated by the nervous system. These will act as pacemakers for sheets of muscle tissue. The rate and intensity of contraction can be modified by the nervous system or by external chemical stimuli. When nervous stimulation generates an action potential on the cell membrane, the sarcoplasmic reticulum will release calcium, and extracellular calcium will also enter the cell from the caveoli. We have a slower contraction rate in smooth muscle because it takes a while for the calcium to accumulate. Just like in skeletal muscle, calcium is necessary to trigger the myosin-actin interaction, the sliding filaments, but it happens in a different way. Calcium binds to calmodulin, and this activates calmodulin. Activated calmodulin activates an enzyme in the cytoplasm known as myosin light chain kinase. ATP is on the myosin head, but it hasn't been split. This means the myosin head isn't in its cocked position. Myosin light chain kinase is necessary to split the ATP on the myosin head so that the myosin head can cock and then attach to the actin. Once we have the cross bridge formation, the filaments will slide. The myosin completes its power stroke and then it releases. So we have the action potential allowing calcium to enter the sarcoplasm from both the sarcoplasmic reticulum and externally, and it binds to calmodulin, activating it. Activated calmodulin will then activate myosin light chain kinase. This will split the ATP on the myosin head, activating it, putting it in its cocked position. And in this case, there's no barrier between the myosin and the actin, so the myosin can directly attach to the actin and the filaments can slide. When the smooth muscle relaxes, it's because nerve stimulation has stopped. Calcium is pumped from the cytoplasm, both outside the cell and back into the sarcoplasmic reticulum. Just like it took a little while for this calcium to come in, it takes a little while to get the calcium out. So the contraction of a smooth muscle is a little slower to start, but it stays contracted for a little longer. There's also a very low ATP requirement for smooth muscle. Smooth muscle can stretch more than skeletal muscle, and it has something called the stretch-relaxation response. Basically, when you first stretch it, it wants to try to contract right away, but then it adapts to that new length and it relaxes again. This allows for organs to fill completely. Smooth muscle does have some ability to divide throughout your life, so it can experience hyperplasia. That is, it can make more muscle cells. This is what happens in, say, a pregnant uterus when we have to make more smooth muscle as the uterus expands. Skeletal muscle tissue develops from myoblasts. These are the embryonic muscle cells. These become amitotic, which means skeletal muscle loses its ability to divide as maturity occurs. There are a few satellite cells in skeletal muscle, so there's limited regeneration, but it's very, very limited. Smooth muscle regenerates throughout your lifetime. The somatic nerves control skeletal muscle. A newborn's first movements are reflexive, but all of your skeletal muscle control improves with age. Maturation occurs anterior to posterior. Babies can control their heads before they control their feet, and from medial to lateral. Babies can wave bye-bye long before they can pick up Cheerios with their fingers. In terms of male and female, the muscle mass varies. Women are about 36% body mass is muscle. Men have about 42% of their body mass is muscle. The strength per unit mass is the same, but because women have less mass, they appear to be less strong. Strenuous exercise can cause greater muscle enlargement in males than females, primarily due to testosterone. Anabolic steroids are basically testosterone. They're synthetic male sex hormones that some people take to try to increase the development of muscle mass. There are some problems with this. As we age, the connective tissue and muscle increases. Tendons and ligaments shorten and weaken, so we lose flexibility. By age 30, we're starting to lose muscle mass. This is called sarcopenia. Regular exercise can help reverse this. There's a loss of strength as we age. By age 80, we're 50% less strong than we were when we were 20. The aging cardiovascular system will have its effect on muscles. Blood will not circulate completely through the muscles, and this will mean that the muscles are not adequately nourished. Some people experience intermittent claudication. This is when they have atherosclerosis that restricts circulation, and when they walk, they get severe leg muscle pain. Smooth muscle is fairly trouble-free throughout life. Muscular dystrophy is a disease that causes the muscles to enlarge due to fat and connective tissue deposits. As the muscle fibers atrophy and degenerate, muscle control is lost. The most common type of muscular dystrophy is Duchenne muscular dystrophy. This is a sex-linked recessive disease that affects mostly males. It starts in the feet and works its way up. Usually these individuals die of respiratory failure sometime in their 20s. Muscles lack the fiber dystrophin. This is the protein that links the cytoskeleton to the extracellular matrix, stabilizing the sarcolemma. Without this protein, the muscle cannot remain healthy, and the cells begin to deteriorate and degrade.